Ladies and gentlemen, get ready to inspire by Lachezar Lechev. Lachezar is passionate about space exploration and challenges it brings. He's a community manager for AeroRust and works tirelessly to promote Rust programming in the aerospace field. With love for open source and a talent for bringing people together, Lachezar is here to spark your curiosity about the future of aerospace. Please join me in welcoming Lachezar Lechev. The stage is yours.
Thank you very much for the introduction. Hello, everyone. Let me see the clicker. Yes, clicker is working now. Today, I'm going to tell you how to get started with embedded Rust, and this is the nanosat edition. This is only part one of the presentation. I'm going to tell you a bit more about that later. First, I would like to take this opportunity to thank the organizers of the UARust Conference. I'm very happy that I can bring such support to Ukraine and hopefully help people that are suffering the war. And just massive congratulations to the people organizing the conference. I know how challenging it is, so good job, everyone. Now, we have a small agenda for today, small. First, I'm going to tell you about who am I and why I'm standing in front of you speaking about this. Then I'm going to tell you a bit about the AeroRust community and some of the projects we are building. Then we're going to take a look at the tools. This is the main part that we're going to be drilling down. And at the end, I'm going to give you a conclusion. At the very, very end, I have prepared a special demo, which is part two of this, but more on that later. Now, I'm usually the person that you must come and speak to if you want to build a spaceship. So I'm very excited about aerospace, as the introduction said, and I usually love a challenge. My name is Lachezar Lechev, and on most places you'll find me as LPL. On X, you'll find me with an underscore. And if you want to reach out to me, DM me, there's no problem. Just reach out. I'm always happy to help. Apart from being a developer and software engineer, basically, I'm also a community manager of the AeroRust community. I've decided to link just the URL of the community website because there you'll find also the Discord invite, which is our main place for gathering. We also have a blog and a newsletter that's hopefully coming soon. We do want to share more technical blog posts, and also in the newsletter we want to include some of the resources that our members are sharing in the community, and just condense it and present it to you so that you can ingest it with your pace without following the community. But as always, it's better to just join the community and learn by doing. It's a good place to mention that we are welcoming everyone. This was the attitude that I felt from the Rust community when I started writing Rust, and I wanted to keep this notion in the AeroRust community as well. So there are no dumb questions. There are no beginner. I'm beginner. I cannot. I don't know what I'm doing, because everyone is there to learn and develop together. So definitely join in. Now, the workshop started as an AeroRust run workshop at Space Conference Plovdiv in 2023. We set out to build a very small workshop. And on the right, as you can see here, there is a picture of people assembling the frame. On the bottom right, you see the kit that you had to assemble, basically, with a breadboard and two microcontrollers. And on the bottom left, you see the whole all the components needed for the workshop. We're still working on it, but that's why I'm here to tell you more about it. We do have a few other projects currently in the community which are active, but we're going to be speaking about the nanosat workshop. Now, let's see, clicker stopped working. Come on. So before we created the workshop, of course, we had to set up some goals. And there were three main goals that we had to tackle. First of all, of course, the workshop has to be accessible. So anybody should be able to source the material, source the microcontrollers, and be able to go through it. The second is that it has to be beginner friendly. So if you know a bit of Rust or more Rust, and you want to get into embedded, this should be the workshop for you. And of course, it has to be a complete package or a complete workshop. And that pretty much drove the decisions on what application we should build. Of course, on the left, you see that we had a few crates that we wanted to use. Embassy, Probar is for flashing, and a hardware abstraction layer. And Embassy, we're going to talk about it in a bit. So we'll just skip that for now. And on the right, you see that at the end, the workshop had to should have cohesive exercises. Also, it should have some kind of functionality. And above all, it should be useful. So a complete application that maybe it's dumb, but still does some kind of functionality. And you can take it from there, develop it further. Now, the main thing that we're going to talk about is the onboard computer. Well, that's how they call it, a computer, but it really is a flight controller, which means that it doesn't have an operating system. You want the low-level stuff to be very near the hardware, right? And in the conclusion, we're going to be speaking about space applications and why you don't want an operating system or as small as possible operating system. And that's actually where our firmware resides, so the onboard computer. And of course, you must have some kind of a power system, so to be able to charge the batteries and also a battery to power everything together. Now, of course, we are going to focus on the firmware, and that's where we have gathered here today to speak about. And our firmware, we decided to have a few components that we wanted to integrate. The first one being a GNSS receiver. So GNSS stands for Global Navigation Satellite System. There are a few constellations, for example, Galileo and GPS, but there are others as well. We wanted to have some kind of a radio. So the GNSS receiver, of course, sends data in a given format, and you want to parse that in order to be useful to us in the application. Then we wanted to have some kind of a radio, so a way to send the data or information remotely or wirelessly to our kit and back. And for this, we're using currently Wi-Fi, but we want to add other kind of a radio, of course, to reach further. And of course, there should be an IMU. IMU stands for Inertial Measurement Unit, and this basically gives you 9 degrees of freedom, which means that you have an accelerometer, magnetometer, and gyroscope. You can say how you're orientated, how you're moving in space, and do other stuff with that information. Apart from that, we have a separate sensor, which is a pressure and temperature sensor. And last but not least, in the exercises, we wanted to include a way to get the battery percentage, which there's a very simple way with very few components that you can use to do this, and we wanted to include it. Because if you know the battery percentage and it's dropping, maybe you want to turn off a given peripheral or a given task in order to conserve some battery before the battery gets charged. And when we're talking about nanosatellite, we actually want to build very expensive nanosatellites. Although in the last years, the price has go down very much, but it's still very, very challenging to first prepare a nanosatellite, go through all the environment tests, go over the legal stuff, and then still pay for a launch, and then go over the whole operation once it's in orbit, if it works. Because most of the nanosatellites sent don't usually work. especially from universities that are just launching their first, second, or third nanosatellite. There's high chance that it won't work. On the right, you see the atmosphere levels. The atmosphere layers, and it's interesting that common line is on 100 kilometers, which means that space is where 100 kilometers officially starts. But in order to get to orbit, you need to travel very fast sideways, right? It's not just going up there and staying there. And there is a very interesting part of the atmosphere. Let me just zoom in for a bit. And this is the stratosphere, this part here. It's very low to where we live, right? But most of the atmosphere there is just below you. So there's very little atmosphere. The weather, you actually don't have that much of a weather. You don't have thunderstorms, you don't have clouds forming and so on. So it's very calm, even if there are winds and stuff like that that can carry you away. And this is where usually weather balloons travel. They can go up to 50 kilometers. Now, I've marked a few interesting things that you can notice. For example, that around 20 kilometers, it's like minus 55 degrees outside. So it's very cold. And also, you do get a bit more radiation, of course, up there. But most of the atmosphere is, again, below you. As you can see, Mount Everest has only 28% of the atmosphere pressure. And the more you go up, the less it becomes. Now, okay, we know that the stratosphere is a good point if we don't want our thing to just float everywhere rapidly or be brought down because of weather. But the question is, how do we get there? Well, I actually gave you a bit of information already about that, and this is using helium balloons, of course. Although it's not inspired by the movie Up, it's still a great concept. And if you take a look at that idea online, you'll find a lot of information, including that NASA builds these giant super pressure balloons, which are meant to stay in the stratosphere for even months, and they have a very high payload capacity because these are like huge balloons. They're special kind of balloons, so they stop expanding at some point. And on the right, you see the more traditional approach, which is using latex balloons. They usually go to a certain point, and of course, because the latex expands, they just burst at some point. And of course, you retrieve it with a parachute, your payload. Okay, we know how to get there. We have an idea what to build. Now, the question is, how do we actually start setting up our project, right? And the first thing that we're going to talk about is Embassy. Embassy, you can call it a framework. I usually like to call it a collection of crates, which allows you to write asynchronous firmware. And just a quick note on the right, this is shortened and taken from the Embassy repository. So if you're interested to learn more about all these topics, just check out the Embassy repository. The idea of putting them here as a list on the right was to give you an idea how much stuff come into Embassy. And the first thing that you'll notice that there are quite a few hardware abstraction layers that support Embassy. And there's STM32 microcontroller support, there's Nordic Semiconductors, there's the Raspberry Pi RP2040, even Expressive Systems has support for asynchronous and Embassy in their ESP-RS hardware abstraction layer. Now, we have good support with MCUs, okay. We know it's an asynchronous, for writing asynchronous firmware, so it has to have asynchronous executor. And of course, how you run stuff on the executor is with tasks. There is a bit more information about tasks and the executor because of how much space you have on a microcontroller, but it's out of the scope for this talk. And there are already production uses of Embassy. I myself have used Embassy for a client's project related to aerospace. And of course, as any project, as any software solution, there are drawbacks. And I would say the main drawback with Embassy, well, I can split them into two, basically, two things, two drawbacks. One of the things is that if your driver crate, let's say you have a sensor, there's a crate for it, but the API that the crate has is only blocking. And now all of a sudden you have asynchronous executor tasks and everything, and now you have to handle blocking operation. And you need to be very careful with that in your application. And the other one is, of course, you're dealing with async await, so it might not be very intuitive for beginners. Okay, we have one of the main tools that we're going to use, but now how do we actually set up the project? First, yes, let's talk about the microcontroller and the architectural support. Initially, for the workshop that you saw pictures from last year, we began with the Espressif C3 board, the Rust board down on the right. And the one that we are currently using for the onboard computer is the Raspberry Pi Pico W, which includes a Wi-Fi chip, which we use currently for the radio. And you will notice between the two platforms that first you have a different architecture. One is ARM, the other one is RISC-V. Then the Raspberry Pi Pico has 2 cores, and ESP32 has single core. And this is challenging if you want to build the same application for 2 platforms, right? How do you support that? And this is where, well, feature gating comes into play. I'm starting with the simplest example that you can have 2 exclusive features in your project. And I've taken this example from the crate for the Wi-Fi chip from Embassy for the Raspberry Pi Pico W. And you can see here that if both features GFMT and lock are enabled, then this compiler error gets called and you get the compiler error. So you cannot even compile your project if you enable both features. Now, the other thing useful with feature gating is that you can use aliases. And not only for features, you can use it for, as you can see here, typing less. We can set out to, for example, build or run a specific binary, enable given features, specify the target that we want to run or build, or just build a documentation for one of the projects, which is very, very useful. So the config.toml is your friend. By the way, I forgot to mention on the previous slide that the nanosatellite workshop, you can find the link down below. But also there's going to be a QR code at the end if you want to grab the slides as well. Okay, you have aliases. What else do we have for setting up our project? Of course, here you can see we already support the Pico and the ESP32, and we separate them using aliases just to ease our life. Well, other thing that you can do in your config.toml is set up default environment variables, specify specific runner. In this case, for the RISC-V platform, we use ESP Flash to flash our firmware on the device. And for the Raspberry Pi Pico, we use probeRS. Of course, you can also add other stuff like Rust flags, or when you're building, you can add Rust docs, doc flags, and so on and so forth. So really take advantage of that when you're setting up your project. How do you set up peripherals then? Of course, feature gating, we already discussed that. But let's see how we actually do that in the code. Here I've taken an example of the main structure and the application structure, which is for the Raspberry Pi Pico. And as you can see here, we can enable the I2C peripheral for field in the struct with more than one feature. In this case, we only need when it's running, when the IMU is running. So that's why we only add one feature. And this will basically remove the field if we haven't enabled this this feature, sorry. Now we have the peripheral. How do we initialize it? Well, the same way. When you're implementing the application and you have some kind of a constructor, in this case, it's a init function. Again, use config feature to enable this peripheral. Spawning a task, the same way. You have the spawner, you have the executor can give you a spawner, and you spawn this task only when the run IMU feature is enabled. And last but not least, you have the task itself. You already can see this embassy executor task macro attribute here. And of course, you can add documentation. In our case, for the workshop, apart from this information that you have for how to calibrate the sensor, we would like to add more information on how to actually set up or go over the exercises. So we're going to have different exercises, and more information about how to make the exercise will go here. Okay. Now, in conclusion, target dependencies versus feature gating. I've seen mostly in the community that feature gating is used. Maybe you can do specific things with target dependencies, maybe to get messy. You have to try this for your own project, see if that setup works well. But feature gating, even in Embassy, it's very pronounced. And it's more flexible in the way that, as you saw in the beginning, you can have two exclusive features, so only one can be enabled. But both are supported for your architecture, your feature. Then real-time Linux versus Embassy. Well, I told you that I'm going to talk about more about operating system versus running something on bare metal. On bare metal, you still can have operating systems, but Linux is generally considered a very large operating system. And even though it's real time, there's only preemptive tasks, which means that you have to deal with the whole complexity of the whole Linux kernel rather than just your specific application. And there's very interesting things when you get to space. There are high energy particles, which can turn your 1 into 0 or your 0 into 1, hit your storage, do some damage, right? And the larger the die of the CPU or the memory size or the code size even, the more likely is this to happen and some catastrophic failure to happen. Of course, the low-level system are built robust in a way that they're redundant. You can do the same thing with Linux. There are companies in the space industry that, for example, run up to 3 redundant systems or 3 redundant kernels doing the same thing, and then they start comparing to see if one of them is wrong, for example, to take the right value. Okay, so Embassy is ready for you. Linux, there's still place for it, right? But now on to the last point. And this is a special demo because honestly, I'm very, very lazy and I don't want to carry this hardware all the time. So this is the kit that we're developing, and you have to carry all the things all the time with you if you want to debug or just do things. So why not just work on remote flashing, right? The more complex demos and examples will be at Expressive DevConf 2024, which is in September. So definitely make sure to come along and see the second part of this talk. But now let me show you the quick example for today. Now, first, what we're going to see. In this case, we have the laptop. It's going to run both a server and a client, just to make things simpler. But the server can as easily go on a Raspberry Pi, be CI or continuous integration somewhere, doing with connected hardware to it and doing some kind of work on the hardware. But for now, we're just dealing with this laptop. So first of all, I have prepared here the server. I'm just going to run it. There's some configuration file that does a bit of like how do you authorized and so on and so forth. What kind of debug probes you have connected or can connect to and so on. And on the other side, we have the client. For this example, I'm using the Embassy ADC example, which is a peripheral. And this is the one that you can use for, reading out the battery percentage. But let's try to flash it remotely and see what happens. So now here, nothing happens. I'm still working on it. But on the other terminal, you will start seeing these logs that are coming from the embedded system. And you can see that we have 38 degrees. This is an onboard temperature sensor on the RP2040. Here it's giving out error just because this tool is specifically made for running CI. So there is a limit of how long your task should run, and this task just runs forever. So that's why it's giving an error. But you can see on the client side, we eventually got all the logs from this job. So that's good. We still have some output from the server. And yeah, we just run remotely, flashed our hardware. And with this simple demo, I think I'm finished. Thank you for your attention. You can find the slides in this link, or you can scan the QR code. Thank you very much.
So Lachezar, thank you so much for your presentation. It was very interesting and very, like, how to say, it provided a lot of interesting new information. We actually have a lot of questions in Q&A. I'll try to prioritize them appropriately.
Mm-hmm.
So it's,
you're going to read them out, right?
Yeah. So how does Embassy framework facilitate asynchronous development in embedded projects?
How it allows it, or
yeah.
Yeah, basically whenever you're waiting for something to happen, let's say an interrupt to get triggered or some information to come on the USB, for example, the executor actually changes tasks and goes to something else. So that's the power of asynchronous programming, right? And that's why having a blocking driver is actually a very big deal, because you have this asynchronous executor which can do a lot of stuff. A lot of tasks can run on a single core and be switched, right, by the executor. But the moment you have something blocking and takes more time than usual, then everything after that starts failing, right? You expect, for example, the sensor to be called every 5 seconds. It starts getting, or every 2 seconds or 5 milliseconds or whatever. And at some point it starts getting called less often and less often. So this is a challenge.
All right. So, but the Embassy framework itself does not have asynchronous primitives.
Primitives, what do you mean as a primitive?
Like something which returns a future or an executor.
Yeah, there is the executor, and basically you can have asynchronous functions as tasks. There are some limitations, you have to check them out. And how Embassy works underneath, yeah, it's a different topic that I don't want to get into right now.
Okay, that's fine. Are there any challenges in supporting multiple boards in a single project, and how can we overcome those challenges?
Yes, so we started with the Espressive board, and later I decided to add support for the Raspberry Pi Pico, which is a challenge and still is a challenge because you have to set up all the features correctly and in a way that allows you to be flexible. So this probably was the biggest challenge and still is the biggest challenge, just dealing with all the features. For example, the embassy executor for the Pico needs one feature, for the expressive board needs another feature. What I personally did for this project was to have the onboard computer application and then two separate crates, which have their own application struct, which gets called at the onboard computer one. Why I decided to do it this way? Well, just adding support for both platforms at the same cargo TOML file will be a challenge, and you have a lot of dependencies. So I decided just to split the dependencies in their own crates, right, for the different applications, the two different applications, but be called in the top application, the onboard computer. That's how at least I've set up the multi-board support.
All right, understood. Thank you. So the next question, the person asks, Bogdan asks, I know that Pico has PIO. I assume it means programmable I/O. Does ESP have something similar? If yes, is there an abstraction layer for it?
So Expressive is taking on the challenge to support their community, the Rust community. So they're doing all the work for the hardware abstraction layers, and they generally have very good support, even on the no-NSTD version. Shout out to Omar, who probably finished his talk already, but he was the one that came to Bulgaria to perform the workshop with me on the space conference. I think, yeah, I lost my PIO. Yeah, I'm not sure about the expressive. Sorry, I forgot my sentence, but I'm not sure about expressive, but it's very easy to check. I personally haven't used PIO, but it's used for many things, including outside the Rust community. I've seen very interesting applications for the Raspberry Pi Pico. So definitely check out some articles.
Thank you. So speaking of workshop, is the repository enough to complete the NanoSat workshop? Do you think it's a good first embedded project for someone who already has Rust skills?
The goal is to be. As of today, we're still working on the actual implementation. Once the application is done, and we have a set MVP version for the hardware, because we want to support our community with this hardware. So we're going to start selling an MVP product soon. Hopefully by the end of the year, we will have pre-order. So definitely watch out the community and subscribe to the newsletter. But generally, the current version of the workshop is not ready. There have been many problems even with the old version, and with the new version, all the code is there. So we need to remove it and write the exercises to tell you, okay, now set up this peripheral, now do this, and do it in exercises split by sensors, by different features that you can add, and so on.
Thank you. And do you have I know it's a bit of a hard ask. Do you have an estimate when do you expect this to be in a good state?
Definitely for the pre-order, I think we should have something or by the end of the year. Currently, we are focusing on the hardware just because the application itself also has some issues. So we are debugging, testing. We want to fly this kit as well. So, put it on a helium balloon, start testing, because there are many challenges that you need to overcome in order to make it useful. For that kit to be useful, it needs to be doing something useful, right? So you need to be able to put it on a balloon, send it, and for it to survive. Otherwise, it doesn't make sense. But the idea of doing like some kind of a crowdfunding campaign with pre-orders, and also support in that way the AeroRust community and the efforts in the workshop are the way that we're looking to do everything.
Of workshops, can you name maybe a simpler workshop for embedded devices?
Well, there are a few Rust embedded books. online. I know Omar wrote a book about embedded, but workshop like this one that takes a bit more general approach, many peripherals, many exercises. I personally don't know about any, but there might be. So I just haven't looked.
Understood, thank you. Speaking of hardware, does the nanosat include some maneuvering system, or will it orbit until it burns in the atmosphere?
The easiest one is to add magnet torques, which are just coils, winded cores, winded wires that you can use to apply voltage, make basically a magnet, and orientate the satellite based on the magnetic field of the Earth. Currently, our one is very simple. It's made to be accessible. We are trying to make it as simple as possible and as easy as possible. But for different applications of these kits, not even in space, but as you saw, the stratosphere, we have a few applications, and we are starting to look at propulsion as well. So a way to control where the balloon goes, which can be very useful if you have specific payload on and you want to put it in a specific place. So it opens a few challenges, but it's also a lot of things. You don't need Starlink, right? If you put the right antenna and and power on this thing, it will undercut Starlink, for example. Why orbit, right?
Right. You're absolutely correct. So, does your system use bare metal, RTOS, or some embedded OS?
So Embassy is the framework that you're using to build your firmware. So you don't have any operating system, no real-time operating system. And Embassy does support preemptive tasks. So you can have one executor with low priority tasks and one executor with high priority tasks. But I personally haven't used that. So definitely check out the Embassy examples.
So, do you know which microcontrollers are popular in nanosats?
From my limited knowledge, I know that some of the startup companies are using STM32 as a microcontroller for their systems. For the rest of the rest of the industry, it really depends. Some are using common off-the-shelf components, universities, and so on. Some decide to use radiation hardened or radiation resistant chips, which are generally with less power or less capabilities, bigger, but are very, very reliable in these tasks. So it really depends which route you decide to go. I haven't dealt with radiation hardened or radiation resistant chips, but you can find information online.
All right. And the last question, what strategies can be employed to integrate Rust with legacy embedded system that uses non-standard or proprietary hardware interfaces? What references what references AeroRust have?
So for blog posts or other resources that you can check, currently I cannot tell you if they exist, but there are a few people in the community that have worked with, let's say, a C library that provides support for a given chip. One of the people in the community decided to make a driver crate for a radar, a small radar that you can use. And I don't think they wrote any kind of like workflow or how to do it, but I know it's possible. So you can integrate, probably you can integrate Rust in old embedded projects if you steer away of any kind of peripherals and so on, but do some of the logic in Rust and just, cross the boundary. Or you can integrate C into Rust, as we all know. So I personally didn't ever learn C I tried a few times. I failed miserably. It had to be Rust, you know. When you try to learn C for a few times and you fail, and then Rust comes along, and then all of a sudden, yeah. Cool.
Okay, that actually concludes all the questions. So I would ask one more question, which is what kind of result would you expect from a successful microsat launch?
Wow, to work. The first thing is to work and not, you know, launch it and then just figure out that something went wrong. Because even NASA fucks up, right? Even
Yeah.
the big people are fucking up like big time sometimes. But that's why there are processes. There's so much things, I can generalize as things, that you must know in order to launch a satellite. And we're not only talking about the technical part, right? You have all kinds of standards, all kinds of institutions, law, and so on to take upon before you actually launch it. So it's a very, very capital intensive and time consuming effort. So if you launch something and it works, that's the first thing you have to, you know, yeah, cheering for. Hopefully we can get to space. I know it's a very challenging path forward, but that's why we took a different approach, just building something that can still be useful here on Earth to people here on Earth without launching into space. But it is a path forward to actually get our community to launch a satellite at the end. And I
Thank you
think
so much.
that's the
This
goal.
is this was an excellent presentation, and I hope everybody here enjoyed it as much as I did listening to you. And that concludes the presentation, and we can go.
Yeah, thank you very much. Enjoy the rest of the
Thank you. Bye-bye.
conference. Bye bye.